Before proceeding, let's take a closer look at a typical receptacle so we understand how they work. On the surface of this receptacle, you can read the rating in amps and volts. In this case, this is a 15 amp, 125 volt receptacle. Use this one only with a 15 amp circuit breaker. Most receptacles sold today are polarized, grounded, and have two separate outlets. On this type of receptacle, you can see that you have brass terminals on the right side of the receptacle and silver terminals on the left. Also, you notice that this receptacle is polarized. It has a longer slot on the left and a shorter slot on the right side of each outlet. These colors and slot lengths make it easier to understand how to properly wire an outlet. Let's start by analyzing how a receptacle works with the electric current it receives. In this example, we'll properly wire a receptacle that is located at the end of a run of cable. A quick note, electrical devices are found either in the middle of a run or at the end of a run of cable. Depending on where the device is on the circuit will determine how the device should be wired. An end-of-run receptacle is set up like this. Incoming current traveling along the black wire connects to a brass terminal on the right side of the receptacle. Electricity can flow freely from one terminal to the other across this metal tab. So here, you only need to connect the hot lead to one of the two terminals for both to receive power. The white or neutral wire connects to a silver terminal on the left side of the receptacle. So likewise in this case, you only need to connect a neutral wire to one of these terminals for both to function properly. These tabs on the side can be removed to give a receptacle specialized functions. The black wire brings current to the receptacle and essentially waits until a plug is inserted. At that time, the current passes out to the electrical device and returns to the receptacle and continues on to the service panel via the neutral wire on the left side of the receptacle. Again, you'll notice two sets of terminals on this receptacle. You only have to connect one set of the terminals for both outlets to be active. If, however, you would like to put each outlet of this receptacle on a different circuit, simply remove these tabs, and the two outlets will work independently. We'll learn more about this later. Taking a glance at the back side of the receptacle, you may see a strip gauge. This gauge informs you of the suggested length of sheathing you need to remove from the wires to make a proper electrical connection with this receptacle. Normally, 3/4 of an inch is recommended. You may also see that some receptacles have push-in connection holes that allow you to make wire connections by simply inserting the proper gauge wire into the correct holes. Lastly, you see a hexagonal terminal screw at the bottom of this terminal. This screw is commonly green and is the terminal where we connect the ground wire. Often this is labeled GR for ground. You connect a green or bare copper wire to this terminal.
Just a bit of a discussion here on how the animation shows current flowing in these circuits. It could only be described as direct current conventional electron flow is what we're showing here. In actuality, in alternating current, getting way too deep into theory for this course. However, just keep in mind that alternating current flows in both directions rapidly back and forth at 60 cycles per second here on the North American grid. So not important to know that, but just to do know that it is flowing in both directions on alternating current. Direct current is more of a direct current flow, as the name suggests, and it's generally thought to flow from positive to negative, but again, getting way too theoretical. In direct current, electrons actually flow from negative to positive, but that's not important, just a little side note to let you know about those things. Electron flow, alternating current versus direct current. So in the course, we talk a lot about the push-in terminals being used and demonstrate those being used on receptacles and switches. I really dislike the use of those push-in terminals. I've seen more problems with bad connections and such inside the device using those push-in terminals than I do when you make a properly installed connection onto the terminal screw. So we're going to show you some supplemental information that you can click on to see exactly how that's done, but In a nutshell, I like to see that conductor stripped, the insulation stripped off it, a nice hook bent in it, and then put on the screw terminal in a clockwise direction, and then tighten that terminal down on the wire in a clockwise direction, and you'll see why that's important as well. Also, I like to see those unused terminals on devices such as receptacles and switches. If you are using the push-in terminals especially, but if you're using a receptacle and you're only using one set of the screws, I should say, then tighten in the other two screws or any unused terminals, because if you're using metal boxes, for instance, and you're pushing that back in and you happen to get it too close to the edge of the box, those loosened screws and unused screws might touch the box, causing yourself a short circuit. So tighten in the unused terminal screws and don't use the push-in terminals. That's the takeaway here. And when we're talking about stripping wire, they talk about not nicking the conductor. Absolutely. If you nick that conductor a little bit on the copper, that creates a weak point. And if you bend that back and forth a couple times, it's going to break right off. Again, I'll have a link here to some information that demonstrates just how easy that conductor can be broken should you get a nick in the conductor.